How do you know if your machine learning model is truly effective? Model evaluation is the key to understanding its performance. Dive deep into assessing accuracy, precision, and recall. Don't just rely on metrics, uncover insights to refine and optimize. Embrace the challenge of improving your model's predictions. Let's explore the world beyond the numbers and elevate your machine learning game. Today, we embark on a journey through key concepts in model evaluation. First up, cross-validation, the art of wisely dividing data for robust model performance insights. Next, we dive into ROC and AUC, unraveling how to assess and visualize classification model quality. Then, we explore model calibration, unlocking the secrets behind trustworthy probability predictions. Lastly, we delve into error analysis, honing our ability to learn from our model's missteps. Each topic offers a crucial piece of the puzzle in mastering predictive modeling. Let's begin this enlightening exploration. Imagine you build a model to detect rare diseases. It predicts health for everyone with 99% accuracy. But here's the catch: if only 1% actually have the disease, your model learns nothing, it just exploits the imbalance. This is why we need better evaluation methods. Good evaluation goes beyond telling us if our model works, it reveals how and when it works. Understanding this distinction is crucial for developing effective and reliable models. Welcome to Section 1 on cross-validation, where we focus on building reliable estimates of model performance. How can we ensure our models are truly robust? By rigorously testing them through cross-validation. This technique involves splitting our data into subsets, training the model on one subset, and testing it on another. This helps us evaluate how well our model generalizes to new data, preventing overfitting. By embracing cross-validation, we can confidently assess our model's performance and make informed decisions. Remember, reliable estimates are key to successful modeling endeavors. Ever faced the training-testing split problem in machine learning? Picture this: you crave a beefy training set for your model to excel, yet hunger for sufficient test data to gauge its true prowess. But hold on, a solitary split can be capricious. What if your test set flukes out, serving up only cakewalks or nightmares? Enter cross-validation, the hero of the hour. By dishing out multiple data splits, it dishes out reliability. No more flukes, just stable, reliable performance estimates you can bet your bites on. In a nutshell, cross-validation, the antidote to the training-testing split problem. Ever wondered how k-fold cross-validation really works? Imagine your data divided into equal parts, folds, like puzzle pieces. Each fold takes a turn being the test set while the rest train, then rotate. This process repeats k times, with a different fold as the test set each round. For instance, in 5-fold cross-validation, we get 5 performance scores to average for a final estimate. This method maximizes data utility, using it for both training and testing, just not simultaneously. By cycling through these folds, we ensure a robust evaluation of our model's performance. Remember, in k-fold cross-validation, every piece of the puzzle plays a crucial role. Ever wonder why cross-validation is a game-changer for model reliability? It's simple: by averaging across multiple splits, we tackle variance head-on. No more shaky estimates, just solid, dependable insights. Plus, with every data point getting its chance to shine in both training and testing, we make the most of limited data. And here's the kicker: cross-validation acts as your model's personal lie detector, sniffing out overfitting before it wreaks havoc. Sure, it may take a bit more time to train your model k times, but the payoff in enhanced reliability is well worth it. Remember, in the world of data, trust is everything. Ever wondered how to effectively measure the performance of a classification model? Enter ROC curves and AUC. These tools allow us to visualize how well our model distinguishes between classes across all possible thresholds. Picture it as a dynamic snapshot capturing the classifier's accuracy at every decision point. The ROC curve showcases the trade-off between sensitivity and specificity, offering a comprehensive view of model performance. And the AUC, or area under the curve, summarizes this performance in a single metric. Think of it as the overall effectiveness score of our classifier. With ROC curves and AUC, we move beyond simple accuracy metrics, diving deep into the nuances of classification success. Ever wondered how we measure the effectiveness of a classification model? Enter the ROC curve. ROC, short for Receiver Operating Characteristic, unveils the balance between true positive rate, catching actual positives, and false positive rate, mistakenly flagging negatives. It's a delicate dance between precision and cautiousness. Picture this: as we adjust our threshold, we navigate between capturing more positives, a win, and wrongly identifying negatives as positives, a misstep. Striking this equilibrium is key to optimizing our model's performance. Imagine you're navigating through a forest of data, using ROC curves as your compass. A perfect classifier is your North Star, gleaming in the top left corner, distinguishing with precision. Below lies the murky waters of randomness, where classifiers merely guess along the diagonal line. And beware the shadowy depths below the diagonal, there be the classifiers worse than random. Picture the diagonal as a dividing line between chance and skill. Anything above it is a step towards excellence. The closer you sail to the top left, the clearer your vision becomes, separating true positives from the imposters. In this data wilderness, remember, a model's position on an ROC curve reveals its predictive prowess. Aim high, embrace the top left corner, and let your true positives shine. Takeaway: on the ROC curve, soaring to the top left signifies a powerful discriminator, leaving random guessing far behind. What does it mean when we talk about AUC, or the area under the curve? Picture a perfect classifier scoring a solid 1.0, flawlessly separating classes. An AUC of 0.9 indicates excellence, showcasing strong discrimination ability. At 0.7, it's acceptable with room for enhancement, while 0.5 signifies randomness, akin to a coin flip. This single number between 0 and 1 summarizes the ROC curve, reflecting the likelihood that your model will rank a random positive example higher than a negative one. Think of it this way: with an AUC of 0.9, your model will correctly prioritize positive cases 90% of the time. Welcome to Section 3, where we dive into model calibration. It's all about ensuring your probabilities truly reflect reality. Picture this: you've got the data, but how do you make it work for you? Let's uncover the key goals here. We're aiming to grab attention from the get-go, balancing sharp, snappy lines with a touch of depth. No beating around the bush, we want clarity without the fluff. So, think of this as a journey towards precision, steering clear of clichés. Think active voice, vivid verbs, maybe a clever analogy to drive the point home. If things get dense, we'll break it down into bite-sized chunks. And remember, we're aiming for a concise 30 to 45-second insight. In the end, it's all about making those probabilities count. Let's recalibrate and get straight to the heart of the matter. Ever wondered how accurate those 80% chance of rain forecasts really are? Calibration is the key. It ensures that a model's predictions align with real-world outcomes. In the realm of machine learning, confidence scores can often be misleading, leading to incorrect estimations. Calibration bridges this gap, crucial for high-stakes decisions like medical diagnosis. Knowing if 70% confidence truly reflects a 70% probability is vital. Think about it: in critical situations, precision matters. Ever wonder if your model's predictions are as reliable as they seem? Well, let's talk about calibration. In a well-calibrated model, predicted probabilities match real-world outcomes, like clockwork. But watch out for poorly calibrated models; they can be overly confident or downright unsure, like a weather forecast that always misses the mark. Surprisingly, even a highly accurate model can suffer from poor calibration, leading to misleading results. Remember, ranking is one thing, but accurately expressing uncertainty is a whole other ball game. Calibration, the silent hero in the realm of predictive modeling. Why does calibration matter? In the world of medical decisions, doctors rely on accurate probabilities to balance treatment risks and benefits. Legal systems hinge on trustworthy risk assessments for bail and sentencing determinations. And in the business realm, companies optimize spending by predicting conversion probabilities. Calibration transforms your model from ranking to decision-making. Well-calibrated probabilities enable rational threshold setting, cost-benefit comparisons, and confident prediction explanations to stakeholders. So, how can you ensure your model serves as a reliable tool for decision-making? In Section 4, we delve into error analysis, a critical aspect of refining our models. By learning from what our models get wrong, we unlock valuable insights for improvement. Picture this: every misstep is a stepping stone towards mastery. Embrace the imperfections as opportunities for growth. Dive deep into the data, dissecting the errors with precision. It's not about the mistakes themselves, but about the lessons they hold. Uncover the hidden gems and the flaws, refining and enhancing our models with each misstep. Remember, progress is not always linear, it's the detours that often lead us to breakthroughs. Ever wondered how to tackle errors head-on in your machine learning model? It's time to adopt a systematic approach to error analysis. Start by collecting all misclassified examples and categorizing them into false positives and false negatives. Next, search for patterns within these errors. Are there common characteristics or trends that stand out? Then, formulate hypotheses to understand why these mistakes are occurring. Is it due to noisy data or missing features? Finally, take decisive action based on your findings. Enhance your data quality, adjust pre-processing steps, or even experiment with different models. By following this structured method, you can fine-tune your model effectively and boost its performance. Remember, the key to improvement lies in understanding and addressing your mistakes. Ever wondered why your model might be failing? Let's dive into common error patterns to watch out for. Blurry images, missing values, or inconsistent formatting can lead to concentrated failures. Class imbalances may cause rare classes to be ignored or similar minority classes to be confused. Look out for errors clustered near class boundaries, indicating struggles with ambiguous cases. If humans can distinguish cases easily but the model can't, a critical feature might be missing. Remember, the goal is understanding, know why it fails to decide on the next steps. What is the secret to reliable performance estimates in machine learning? Cross-validation. By using multiple train test splits, you reduce variance and catch overfitting early, making your metrics trustworthy. And don't forget about ROC and AUC, they measure discrimination ability by visualizing the trade-off between true and false positives. Calibration ensures meaningful probabilities, so check that your model's confidence scores reflect real-world frequencies. Lastly, error analysis uncovers improvement opportunities by revealing patterns in mistakes. Remember, studying your errors guides you towards better data, features, or models. In summary, master these techniques to elevate your model's performance and accuracy. Let's put your understanding to the test. Why is five-fold cross-validation preferred over a single train test split? And what insight does an AUC of 0.5 provide about your classifier? Consider this: can a model boast high accuracy yet suffer from poor calibration? Reflect on these scenarios. Now, imagine your model is plagued by false positives in night images. What's your next move for error analysis? Engage with a peer to hone your evaluation skills. Remember, the right strategy is key in mastering machine learning.